Hello, I'm Seema from Alobasics. I welcome you all for the next video on wave optics. In this video, let us discuss conditions for well-defined and steady interference pattern and coherent sources. First condition is that the two sources of light must be coherent. First of all, we'll see what are the conditions and then we'll discuss each condition in detail. Second condition is two sources of light must be monochromatic. Then third condition, the two sources of light must have same amplitude, or we say that same intensity. Now we'll move towards fourth condition, that is separation between two sources is very small as compared to distance between the plane of the source and screen. In Young's double slit experiment, we came across the two terms small d and capital D, and this is for those two terms, that is small d and capital D. Next condition is that two slits or the two sources of light should be narrow, and the last condition here is that the two waves should be in same state of polarization. Now all these conditions we'll discuss in detail. Let us start with first condition, that is two sources of light must be coherent. What is meaning of coherent? The two sources are said to be coherent if they are emitting light having a zero or constant phase difference. So you can write definition of coherent sources in this manner. Now if these sources are not coherent, what will happen? Their phase difference will vary with time. And if phase difference vary with time, then position of maxima and minima also vary with time. And interference pattern will change randomly and rapidly. So we can't say exactly where maxima is lying and where minima is lying. And due to that, this is very important condition that the two sources of light must be coherent. Second condition, the two sources of light must be monochromatic. All of you are familiar with monochromatic light. Monochromatic light is a light having single frequency, or we consider it as even single wavelength, or in simple language I say single color. This is also very important condition for obtaining well-defined and steady interference pattern. In Young's double slit experiment, we have seen that fringe width is given by W is equal to lambda d by d. And this fringe width, that is the separation between two consecutive bright or two consecutive dark bands, is depending on wavelength. And if light is polychromatic, wavelength will change from one color to another color, and due to that width will not remain constant. And what will happen? Fringes due to different colors will form at different position and they will not coincide with each other. Means I say that for violet color fringe for bright will be formed here. For red color bright will be formed somewhere else, and there is no matching between them, and due to that the interference pattern which we will get, that will be complex colored or overlapping type of interference pattern. And if we are using white light or sunlight, that will give us colored interference pattern with central bright band. Next condition is related to amplitude or intensity of two sources. And we know that the two sources must have same amplitude or same intensity. This is again one of the most important condition for steady interference pattern. And in video of intensity distribution, we have seen that for bright band and for dark band, in amplitude is given for the resultant one by these equations, where for bright it is addition of the amplitudes, square of addition of the two amplitudes, and for dark band it is subtraction of square of subtraction of two amplitudes. So if these amplitudes are same, we'll get bright band as maximum bright and dark band will have zero amplitude. So it is perfectly dark. Now these equations are from the video of intensity distribution in interference. Link of all supporting videos I have given in description box. As intensity for bright one should be maximum and for dark one should be zero, to get the proper contrast, we consider that amplitude should be same. If amplitudes are not same, what will happen? Then bright will be less bright and dark will not be completely dark, which will result in poor contrast, or that will decrease contrast of interference pattern. And for that purpose, this is very important condition. Next condition is related to distances. And here we say that the separation between two sources, which is small d, be small in comparison with distance between plane of source and the screen, that is capital D. And we know that slit width is given by lambda d by d. You can see this in video of Young's double slit experiment. Link is given in description box. Now in this expression you can see that slit width is directly proportional to capital D, that is the distance between plane of source and screen, and it is inversely proportional to distance between the two sources, or separation between the two sources, and the pattern should be well defined. For that purpose, this D should be large and this D should be small. And for that purpose, this condition is required, or if this condition is followed, we'll get well separation between bright and dark band. Now next condition is the two sources of light should be narrow. If sources are wide, what will happen? The sources or slits, whatever we call, if they are wide, in comparison with wavelength of light. See, wide means, what is definition of wideness? So here we say that in comparison with wavelength of light, in that case, what happens? Each of these slit itself acts as a multiple narrow sources or multiple narrow slits, and they themselves interfere among them, and due to that there is superimposed interference pattern. To avoid this superimposed interference pattern, our slits should be narrow or sources should be narrow. The last condition is the two waves should be in same state of polarization. But this is applicable if light is polarized light. For non-polarized light, this condition is not applicable. Now let us discuss more about coherent sources of light and how to produce coherent sources in lab. We know that coherent sources are those sources which emit light of zero phase or constant phase difference. Means whatever two sources we are having, they must produce phase difference, and that phase difference should be maintained constant. But when we are using different sources, then these different sources emit waves of different frequencies. Even if they emit waves of same frequency, they are not in phase, or phase difference is not maintained constant. Even if initially they are in phase, that phase will not remain same, and due to that, the interference pattern changes every instant of time, and the pattern is not sustained over significant length of time. Positions of maxima and minima are changing continuously. That will not give us steady interference pattern. So, two primary sources or two independent primary sources cannot be coherent, as they emit waves independently, and due to that, their phase cannot be maintained constant. And as phase is not maintained constant, interference pattern will not be steady. And if we want coherent sources, then these coherent sources must be obtained from one single primary source. We consider these coherent sources as secondary sources, and they should be obtained from a primary sources. What are the methods for getting two coherent sources in lab? That we'll see, and we have to discuss two methods of that. Methods for obtaining coherent sources are: first is Lloyd mirror and second one is Fresnel's biprism. We'll discuss this one by one. First method of obtaining two coherent sources from a single primary source in lab is Lloyd's mirror. In this Lloyd's mirror, we have a real source of monochromatic light, and from this source, light is allowed to fall on a plane mirror. A screen is placed perpendicular to this plane mirror. Some rays from this real source are allowed to fall on mirror, and some are directly falling on the screen. The rays which are directly falling on the screen are shown by blue color, and the rays which are getting reflected from the mirror are shown by red color. Actually, as source is monochromatic, all these are single color. Just for differentiating, we are using different colors in this. The rays which are coming directly on screen and the rays which are getting reflected and then coming on the screen, they will interfere with each other to form interference pattern on the screen. This represents interference pattern, and the reflected rays from the plane mirror are supposed to be, they are coming from the certain point which we consider as virtual source. So with the help of plane mirror, we get virtual source which acts as a coherent source for real source. Or we say that real source and virtual source, they are acting as two coherent sources which are prepared from a single source, and here as rays are getting reflected, phase difference is maintained constant, and due to that we say that we are getting two coherent sources from a single source with the help of Lloyd's mirror. The second method getting two coherent sources in lab is Fresnel's biprism. In this Fresnel's biprism is used. What is biprism? Biprism is a combination of two prisms of very small refracting angles. Now here I consider this as a biprism, and this biprism is having this angle which is approximately equal to 178 degrees or 179 degrees. It is too large, so you can understand how small these two angles are there. And it is considered that this sort of prism is made up of two prisms which are fixed base to base. And this prism is having refracting angle very small. This is its refracting angle. This is base of the prism, and refracting angle of this prism is very small. It is about 30 minutes or 1 degree. Now, like this prism, there is one more prism which is placed base to base, and we get such sort of biprism, and this biprism arrangement is used for producing coherent sources. Refracting edge of the biprism is kept parallel to length of the slit, which is refracting edge of the biprism. This is refracting edge of the biprism, which we are not able to show here, and that is placed, or we say that this is placed parallel to the slit, and with the help of that, the upper part or the upper prism and lower prism will form two coherent sources. These two coherent sources will give us light of certain constant phase difference, or rays will be in phase, and we get interference pattern in the shadow region. This is shadow region for the light which is coming from the two sources, and here we observe the interference pattern. Which are two coherent sources here? S1 and S2. These two coherent sources are formed from the single source S. Light from single source is falling on biprism, and it is giving us two virtual sources S1 and S2. So with the help of Fresnel's biprism, we get two coherent sources, and which will give us interference pattern as we get in Young's double slit experiment. Interference pattern is shown here. So in this way, we can prepare two coherent sources in laboratory by using Lloyd's mirror or by using Fresnel's biprism. Here I am giving you few questions on today's topic, and these are the questions for 2 marks or 3 marks. If you solve these questions properly, it will help you for your board exam. Thank you for watching. See you soon in next video.